Hello everyone, we are the TOMA team and today we'll present our project, the non-destructive storm drainage inspection and cleaning robot. Our motivation from this project comes from a very practical urban issue, which is storm drainage systems often get clogged or damaged. And current inspection methods either require human entry or expensive commercial robots. These methods are not always safe or cost effective. Our goal was to build a low-cost, reliable and efficient robotic system that can both inspect and clean stormwater drainage systems, remotely and non-destructively. The primary objective of our project was to develop a robot that can navigate through the typical drainage system pipes and record and transmit visual data from the inside of the pipes, as well as the use of a pressure washer gun to remove blockages such as sediment, leaves, or any other type of blockages that can be inside the pipes. Our robot is waterproof, remotely controllable, and capable of cleaning using an extremely powered washer. Our robot consists of a custom-built plexiglass chassis that houses all our electronics and mechanical components. It moves using 4 DC motors mounted with brackets which we designed and 3D printed. The main control system was built around an Arduino R4 Wi-Fi, which drives the motors and handles basic movement commands. For visual inspection, we mounted a GoPro Hero 9 camera on the front of our robot. This provides us with high quality footage from the inside of the pipe. The gun also is mounted securely on the chassis and designed to remain stable during the cleaning operations. The electronic system of our robot was designed around a central Arduino R4 Wi-Fi, as I said, which acts as the main controller for the movement-related functions. The Arduino receives input from a serial command and outputs PWM signals and digital signals to two L298N motor drivers, each of which controls a pair of DC motors. These motor drivers are connected to the Arduino through digital output pins, which separates channels for speed, PWM, and direction control. Power is supplied through an external LiPo battery pack, which is routed through a voltage regulator to ensure consistent 12 volts and 5 volt lines for different components inside our robot. The motor drivers draw 12 volt from the motors for the motors, while the Arduino uses the 5 volt output from our battery. Each motor driver's power and ground lines are connected in parallel to the main power source, and each motor driver's outputs are wired directly to respective motor pairs, left and right of our robot. We conducted a structural simulation of the 3D printed ABS motor brackets using ANSYS workbench to evaluate their mechanical strength under operation during the operation of our robots. These brackets bear the torque and vertical force from the DC motors and wheels, so it was critical to verify their durability. Also in the simulation, we applied forces equivalent to the expected weight and motor torque during operation. The results showed that the maximum stress values remained within the yield strength of the ABS material, which is typically around like 40 megapascals. The brackets displayed only minor deformation under load. Also confirmed that our structure is safe and reliable for prolonged use in the field. We also performed a simulation on the plexiglass bottom plate, which supports the full weight of our robot and resists the forces from the pressure washer gun recoil. Using ANSYS static structure, we analyzed how the plate would behave under combined vertical loads and the dynamic force exerted by the water jet. The simulation helped us determine the best thickness as well as the hole placements on our plate for mounting components within the robot without weakening our structure. These results confirmed that the induced stresses were well within the yield strength of plexiglass, which is approximately 70 megapascal. Our values are much smaller than that and they are insignificant, ensuring that the plate would maintain its integrity during the operation as well. These findings guided our fabrication decisions and validated our design choices for structural safety. We tested the robot in several phases. First, we verified motor functions and steering control with our Arduino code. Then we mounted all the components and conducted a dry run on the flat surface. Once that succeeded, we moved to mock drainage pipe environment using a large plastic pipe. We also performed theoretical calculations. For example, to mention a few calculations, we used the Reynolds transport theorem to estimate the exit velocity of the water from our pressure gun. It was around 5 meters per second in ideal conditions, which we will show, and 15.7 newtons for the knockback force of the gun. We tested the cleaning function using real debris and evaluated both internal GoPro footage and external footage as well from our point of view to access the performance. While we had some challenges like Wi-Fi instability and component delays, we adapted our approach effectively. Thank you for your attention. We hope you liked our design and presentation.